continue. So before the break, we looked at the benefits of generative models over discriminative models, like right, like when one is useful. So now we're going to talk about discriminant based models versus discriminative models. Okay, so in general, there is a lot of benefit in having access to the probabilities. Okay, so discriminative models like give you P of Ck given X, right? So you don't get this from discriminant based models. So there are many advantages of having P of Ck given X. Okay, so first example, like for example, like if you want to minimize risk, where the notion of risk could change over time. Okay, for example, let's say you start with the 0, 1 loss matrix, something like this, in a 4-class problem. Okay, now you trained a model, you have deployed it, then you find that the model is making this one common mistake that you want to penalize. Okay, just as a hypothetical example, like so for example, like oh sorry, this is not a, it should be the reverse of this. So 0 1 1 1 0, sorry, 1 0 1 1 1 1 0 1 1 0, right? Just as a hypothetical example, like let's say this is a mistake that you don't like your model to do. Okay, and you want to change this to 10. Okay, if you have already trained your model and you have deployed it, right? Now you want to go back and change the loss matrix. It's going to be really hard with discriminant based methods. For discriminant based methods, you have to retrain your model again with this new loss matrix. Okay. However, for discriminative models, once you have access to the probabilities, instead of taking argmax, which is what we typically do when mistakes are equally costly, right? Like so, you could have a separate procedure which tries to minimize the risk based on this new loss matrix. Okay, so it's basically easy to change things like even after training when you have a discriminative model. Okay, so the other benefit of having discriminative models is like you can actually use these probabilities to handle class imbalance. Okay, so for example, let's say I want to do cancer prediction. The problem with cancer prediction is your data is going to have a lot of no cancer and very few cancers, right? So for example, let's say 1 in 100 patients has cancer. So which means 99 data points are for no cancer and 1 data point for cancer, right? So if you train a model with this data set, what could happen? Like, so I have a data set where 99% of data is no cancer and 1% is cancer. And let's say I train logistic regression. So what do you guess would happen?
Going to misclassify.
Right?
It's going to misclassify the cancer.
Yeah, so there are 99% examples for positive, so for no cancer, right? So which means when you do gradient descent with logistic regression, you're trying to minimize the loss for all the examples, but then no cancer is overrepresented, right? Like so you are trying to predict no cancer 99% of the time. So one simple solution for this problem is to always predict no cancer. Because if you always predict no cancer, you're going to get 99% accuracy. right? Is that a useful model? That's a different question. But the point is, when you have class imbalance, you could get into these kind of issues. So how do we avoid this? So what can we do to avoid this? Any ideas? Yeah.
You can heavily penalize false positives or the opposite, whatever.
Yeah, you can heavily penalize the mistakes where the model is predicting no cancer for patient having cancer, right? Like so basically you're changing the weights of the loss function, right? So the other way to do this is actually to sample more positive examples and sample less negative examples. Okay, so basically this is what people say when they say we're balancing the class distribution. Okay, so what we will do is we are going to sample the rare class more, okay, and balance the class distribution. Okay, so then I'm going to learn the posterior probability. Learn the posterior probability. Okay, then I can actually compute new posterior as volt posterior divided by class fraction in sample data multiplied by class fraction in original data. Okay, if you have access to P of y given x, then you can do this kind of things easily. Okay, so the other benefit of having access to posteriors is you can actually combine models easily. For example, let's say I want to do P of ck given x1, x2. Okay, let's say we are working on a medical problem where x1 and x2 are the features based on some tests, and typically these tests are expensive, right? So every new patient that comes into the hospital, you don't want to do every test, right? Like, so you want to start with some tests, and depending on the results, you want to do more tests, right? Which means if I have two costly tests, x1 and x2 to do to predict the disease, can I start with just one test and have the prediction based on that, then combine the second test easily if needed, right? So let's see how to do that. So P of ck given x1, x2 is actually proportional to P of x1, x2 given ck, P of ck, right? That's the base rule. Now this is proportional to P of x1 given ck, P of x2 given ck, P of ck. Okay, so I'm just applying the naive Bayes assumption. So now I can flip the probabilities again and write as P of ck given x1, P of ck given x2 by P of ck. Okay, so what I have done here is essentially applying the Bayes rule one more time for these two. Okay, so now you see I can write P of ck given x1, x2 as product of P of ck given x1, product of ck given x2. So it is enough to just train two models, one for P of ck given x2, one for P of ck given x1, and like x1 and x2, right? Like, so you can use one model with whatever test that you have done. If you want to do a second test, then you can combine the prediction together by using this formula. Is it clear? So the final use of the posterior is you can actually have a reject option in your classifier. For example, if P of c given x is not greater than 0.6, for example, then you can just reject. This is to say that, oh, if my model is classifying something as positive, okay, is it mine? No. Okay, if the model, if my model is classifying something as positive, but the probability is between 0.5 and 0.6, then just to be safe, I'm not going to make this classification. I'm just going to reject this example so that like some human can come in and do the classification. Is that clear? Any questions? Okay, so I think that concludes our discussion on different ways of doing classification. Okay, so now I want to talk about evaluation metrics for classification. Okay, and I want to start with, well, I think I'll do all the discussions with just 2-class problems. You can generalize this discussion to k-class problems. Okay, so let's say I have a 2-class problem where the classes are positive and negative. The most common evaluation metric for classification, which is what we have seen so far, is accuracy. Right? Accuracy is defined as number of correctly classified instances divided by total number of instances. Right? Let's say I have 100 examples and 70 of them are correctly classified, then the accuracy is 70 by 100, 70%. Is that clear? Now, just now we saw the cancer example, right? Like, so typically accuracy is not a good evaluation metric all the time. So the best example is really the cancer prediction task that we saw, right? So let's say I want to do cancer prediction and I have 9,900 patients where cancer is equal to no and 100 patients where cancer is equal to yes. Okay. Now, if I have a classifier which gives a default no as answer for all the x, this is going to have 99% accuracy. Right? That's close to 100%. But can I use this classifier? Can I deploy this classifier? No, it's a useless classifier. Like, so there's no point in deploying this because it is never going to identify cancer, which is what we care about, right? So this brings us to this point that not every error has same cost. Okay, so some errors are much more costlier than other kinds of error. Okay, now in this cancer problem, there are 2 kinds of errors, right? So the first type of error is when the patient has cancer, the model is saying, no, they don't have cancer. The second type of error is when the patient doesn't have cancer, but the model says, yes, the patient has cancer. So which type of error is more costly here?
First one.
Yeah?
The first?
The first one, right? So if somebody has cancer and the model says they don't have cancer, then the doctor is going to let them go home, right? Like, so no more follow-ups. And maybe in a year, they could die, right? Which is a really bad outcome. On the other hand, let's say someone doesn't have cancer and the model says they have cancer. What would happen after? So the doctor is going to ask them to do more tests. So worst case, they are a little bit stressed for a week and paid a little bit more money. But then after a week, like they're going to figure out, like find out through more precise tests that they don't have cancer, right? So sometimes it's okay to make this mistake. Like, so like if you have to have some trade-off, it's okay to have this kind of mistake, like where the model occasionally says someone has cancer when they don't have cancer. But I don't want my model to miss even one patient who has cancer by saying no cancer, right? So now we are going to talk about different types of errors and how do we optimize for one type over other, right? Like, so we're going to use this concept called confusion matrix, okay, which basically tells how confused the model is. Okay, that's the name, confusion matrix. So for a binary classification problem, the confusion matrix is a 2 cross 2 matrix. where in the columns you have the true values, and here you have the model's prediction. Okay, so positive, negative, positive, negative. Okay, so what are these values? When the class is positive and the model is also predicting the class to be positive, right? We are going to call that as true positive. Okay, when the class is negative, the model is classifying it as positive, right? The model is falsely classifying something as positive, so we're going to call this false positive. Okay, similarly, when the class is positive but the model is falsely classifying it as negative, we're going to call this false negative, and this is true negative. Is that clear? Okay, now let's take an example. Let's say I have 100 examples, 60 of them are positive and 40 of them are negative. Okay, if I have a confusion matrix that looks like this, so what does this mean? This means that 40 positive examples are correctly classified and 20 of them were wrongly classified as negative. 30 negative examples were correctly classified and 10 of them were wrongly classified as positive, right? So this tells how much the model confuses between class 1 and class 2, right? Now, how would an ideal confusion matrix look for this example?
So one
Yeah,
would be an identity matrix, like
no, it's not identity. Like, well, look, it is like an identity.
like an identity.
You still have the numbers, right? Like, so you have 60 positive examples, 40 negative examples. So how would the ideal confusion matrix look like? It's diagonal.
Yeah,
like, what would be the entries of the diagonal?
60, 40, and 0.
Yes, it's going to be 60, 0, 0, 40, right? So all the 60 examples correctly classified, all the 40 examples, like negative examples, correctly classified, and there is no confusion between the classes. Okay, so if I have to give you an example for a bad confusion matrix, like maybe something that is like 30, 20, 20, 30, 20, right? So this is ideal. This is bad because there is too much confusion. Is it clear? Okay, so now using this confusion matrix, we are going to come up with new evaluation metrics for classification. Okay, so we're going to talk about two important evaluation metrics that are very common. So one is called precision, the other one is called recall. Okay, so let me write the confusion matrix here. So true positive, false negative, true negative. Okay, so we have precision and recall. So first I'm going to write the equation for precision and recall. So then we will talk about like what it actually means intuitively. Okay, so precision is defined as true positive divided by true positive plus false positive. Recall is defined as TP by TP plus FM. Okay, now what do they intuitively mean, right? Like precision and recall. Okay, let's first look at precision. So precision is true positive divided by true positives plus false positive. Like, what does this mean? So this means that out of all the model's predictions, positive predictions, how many of them are truly positive, right? The denominator there is all the predictions by the model that are positive, both true positive and false positive. Okay, so let's say my model says there are 100 positive predictions. How precise is my model? Like, so whenever the model says someone has cancer, how precise it is, right? Like, so like how many of them are truly cancer, right? So that is what precision means. Is that clear? So if I have to write it down, so precision means out of all positive predictions, okay, how many of them or truly positive. Okay. Now recall. So what is recall doing? Recall is true positive by true positive plus false negative. Okay. So the denominator is the actual positive examples that are in the data set. It's not model's prediction. The denominator here is not model's prediction. The denominator here is actually the total number of positive examples in the data set. Okay. So then the recall asks, out of all the positive examples that exist in my data, how many of them can my model correctly predict as possible? Okay, so this is like asking how good is my model in recalling the correct examples. Okay, so if I have to write it down, so out of all positive examples in the data, okay, how many of them are correctly classified by the model? Is that clear? Now let's try to understand when to use what, right? Like, so when is precision useful, when is recall useful? Like, so just as a recap, precision means whenever my model makes a prediction, it is accurate, right? Recall means whenever something is positive, my model will definitely predict it correctly. Okay, now tell me example applications or situations where, give me one example where precision is more important, give me one example where recall is more important. Yeah. For cancer, which is important? Recall is very important for cancer, right? By the way, they're both important in general, okay? Like, so it's just that one is more important than other, okay? So like in the case of cancer example, recall is really, really important. Like, so if someone has cancer, I really want my model to predict that correctly, right? Now, can you give me an example where precision is more important? So when is being precise more important? Yeah. Okay. Any examples? Yeah.
I guess it'll be a situation where when you predict something is positive, it really has to be positive. Would that be the interpretation?
Yes.
Okay. So I guess like, let's say some sort of surgery is really expensive, something like that,
Okay.
or some sort of test. If you predict positive and you go through with it, you really want to make sure that it's actually the procedure or whatever. If there's a high like base cost or something.
Well, the worst case is you pay more money.
Right. So let's say you're money sensitive or whatever.
Okay. Okay. Yeah. Okay. Any other example? I think it also depends on the nature of the disease, right? Like, so, yeah.
Maybe when no one someone
Okay. I think you're all still thinking about medical applications. So, yes, think about other domains, like, so, yeah. Okay, so investing, yeah. So you need to be highly precise if you want to invest, yeah. But another example, like, is like your iPhone face password systems, right? Like, so I guess you all use your facial recognition for passwords, right? Like, so this is an example where if you really care about privacy of your phone, like you want the system to be highly precise. Like so, like you want, okay, sometimes it's okay if it doesn't recognize your face, because worst case you can always type in your password, but it is not okay that it recognizes someone else's face as your face, right? So it, like here you really care about precision. Like so, like it's okay once in a while it doesn't recognize your face because typing the password is easy for you, right? Like so. On the other hand, the risk of someone else being able to open your password is, or maybe they can use your bank app, like, or anything else that you have to get money or other things, right? Yeah.
I was going to ask, does precision matters for like bank application stuff, like fraud transaction or?
Yeah, it's a generalization, but yeah, you could say that, like for bank related things, maybe yeah, like well, I can always find counterexamples, but yes, like these kind of money. Your example also is a little bit money oriented, right? Like so, all these money based things, like so, you want to be more precise because the risk is losing money. You don't want to lose money, right? But you can think about other applications, like maybe as an exercise, think about a bunch of prediction problems and like ask this question, like, is it important to be more precise here, or is it important to be more recall? But at the same time, like as I said before, it's not enough if you have a model which has 100% recall but zero precision. Okay, it's actually very easy to construct such a model. For example, instead of having a model which by default says no cancer, you can also by default say yes for cancer. So that model is going to have 100% recall but zero precision or close to zero precision, right? So yes, one is more important than other, but in a lot of applications, like they're both important. Okay, so which is where like this other metric comes into place, which is called F1 measure, which is basically a geometric mean of precision and recall. It's 2PR by P plus R. Okay, so if you have a system that has very high F1 measure, it means you're giving more, like you're kind of giving importance to both precision and recall. Like it's going to have high, you can increase F1 only when you increase both precision and recall. Is that clear? Now, as an exercise, I want you to think about how to extend all these measures for more than binary class problems. Okay, so it's very easy, or if you can go read about it as well. And for your Kaggle competition, you're going to use like a version of F1 measure, like macro averaged F1 measure for a multi-class problem, I guess. Okay, so that's what I recall from reading the statement. Some version of my F1 measure. Is that clear? Any questions so far? Okay, so now let's start with decision trees. So we are going to continue learning more classification algorithms. Okay, so we will start with decision trees today, which is a non-parametric method for classification. Okay, it's going to be very different from all the classification algorithms we have seen so far. Okay, because so far we looked at model-based approaches, like where we come up with a mathematical model, like some equation, and whenever you want to make prediction, you feed in X, you compute the value, you get some prediction, right? So now we are going to look at some model like which is more symbolic than mathematical. Okay, so here is an example of like a decision tree. Okay, so first let's start with the problem. So this is the problem. This is the running example for today's lecture. Okay, so in this case, this is a banking application, like where like the bank, let's say, wants to develop a machine learning algorithm to predict whether someone will default their loan or not. Okay, like usually when you apply for a loan, there is a classification algorithm which decides whether you are a safe person or risky person. If you are a risky person, then you get rejected, like from the loan application. And if you are considered to be safe, then a human will come in. They're going to look at your profile in more detail and decide whether they want to give loan, right? So almost all the banking applications, like almost all the banks nowadays have an AA screening before it even goes to a banking manager. Okay, so what does this application look like, right? Like, so here they get a bunch of information, like, so for example, whether you already own a home or not, right? So this is a categorical feature, like it's either yes or no. So then what is your marital status, right? Like single, married, or divorced. Your annual income, right? So depending on these three features, I'm classifying every candidate as defaulted borrower or not. If someone is defaulted, then you don't want to give loan to them. Okay, so that's the problem. Is that clear? Okay, so given a data set like this, let's say you want to do logistic regression. So how would you go about doing a logistic regression for this problem? Yeah. The features are all not numbers. It's not a vector, right? So how would you do logistic regression here? Yeah. Yeah, so you're going to convert these things into numbers. Like homeowner, you can make it 0 or 1, right? For marital status, what would you do? So there are 3 values. You can make one hot representation, right? Like you can have 3 features. The first feature saying, oh, whether someone is single or not. The second feature saying someone is married or not. Third feature saying someone is divorced or not, right? So then you have the annual income, right? Like, so it's a large number, so maybe you can normalize it or standardize it, right? Like, so basically you can construct a vector with all these features, right? Or derived features from these features, and it is a binary problem, 0 or 1. So if you want to do logistic regression, you can do logistic regression here, right? So instead of doing that, like what we are going to do is we are going to construct a tree, a decision tree, which looks like this. Okay. First of all, let's try to understand the syntax of the decision tree, right? So typically, the decision tree is going to have some conditions that you're checking, and depending on the outcome of this condition, you move in the tree. Okay. So for example, this tree says, oh, given a new customer, you check whether they are homeowner or not. Okay. If the answer is yes, then you go here. The tree ended here, so there is a leaf which says no, which means if someone owns a home, they're not going to default the loan. So you can trust the person. Okay. If the answer is no, then you check the marital status of the person. Okay. If the person is married, then this tree says that, oh, you can trust them. They're not going to default the loan. If they're single or divorced, right? They don't have a family, so like they could take risks. So then you need to look at their income. Okay. And if their income is greater than 80K, then they are safe to, well, no, actually it says if their income is greater than 80K, there's a chance that they could default. Okay, the loan. If it is less than 80K, they won't. Okay, some interesting way of classifying the applicants, right? So once you have access to, okay, first of all, we need to discuss how to learn a tree from the data, right? That is what the learning part of the algorithm is going to be. We will talk about it today. But for the moment, let's assume that someone has given this tree for you. So given the data set, someone is giving you this tree, right? How can we make use of this tree for new examples, right? Like, so for example, let's say a new applicant come in, and this is their status. Okay. So how would you use this tree to decide whether they are going to default or not, right? So you will start with homeowner, right? So for this person, the homeowner is no. So you go this way, right? So then you check marital status. So this person is married. So you go this way. So now you have already reached the leaf. You don't need to check the taxable income. Like, so you know the answer. The answer is no. So this person is not going to default. So they are not going to cheat. So you could give loan to this person. Is that clear? Any question? Okay, now here is the interesting part, right? Like, so how do I come up with a tree like this from the data? that we have. Any thoughts? So how can I construct a decision tree from the training data? Yeah. Sorry. Okay. Oh, but that is okay. So we used KD trees in KNN just for efficient indexing purposes, right? Like so here, this tree serves a different purpose. This tree here, the tree is actually the classifier, right? Like so, you want the tree to have as high accuracy or better generalization as possible, which is a different goal. Yeah.
Go through all the possible splits, so for each feature, and then we pick the one that maximizes entry.
Okay, so the suggestion here is to go through all possible splits and find something that is better for whatever we care about, right? So why do you think homeowner is the first test instead of marital status or income? Anyone? Yeah. Yeah, it's actually already a better split because you look at all the places where the homeowner is yes, right? So you see the answer is always no, right? So if I consider this particular split, then there is one subset where the answer is clear no. You can check the other two splits, you will not get such clear separation. So ideally, we are looking for splits which will give clear separation of yes and no, so that we can more confidently say, oh yes, this is no. Is it clear? Yeah. Yeah. Okay. So yeah, we will come to that. Like I think you both gave some suggestions. Like, but in general, I think the crux of a decision tree algorithm is to come up with a metric which says, oh, this is a good split, this is a bad split. Okay. So once you figure out such a metric, well, there are many such metrics that exist. Okay. So once you figure out such a metric, so then you can construct a recursive algorithm which says, oh, let's consider all the tests, find the one which maximizes this metric, right? That is my first test, first node, right? Once I do the first node, then I can repeat the same process with other tests and repeat until I reach all yes or all no, or until I reach a place where it is clear that this is yes or no, right? So this idea, right, like so of recursively finding the best split, right? So this is what the core idea for coming up with a decision, like with a decision tree, and this is called Hunt's algorithm, mainly because he came up with the first version of decision tree, but then there are hundreds of variants of decision trees. Okay, so what we are really going to do in this class today is to just talk about the general idea of decision trees, but then you can find different flavors of decision tree. There's CART, there is C4.5. There are many names for different variants of decision trees. Okay, so it doesn't matter that you should know exactly what CART is doing or what C4.5 is doing. Like what really matters is you know the general principle behind constructing these trees. Okay, for specific instantiations of the algorithms, you can always go read the papers, but you can also explore them in scikit-learn. So in scikit-learn, like you can actually choose which decision tree algorithm you want to run as a hyperparameter. Is that clear? Okay, so what is Hunt's algorithm? So the idea of Hunt's algorithms is really simple. So if, okay, so we're going to start with some data set, right, which is a bunch of yes, no, right? If dt contains records that belong to the same class yt, then t is a leaf node labeled as yt. So if at all I reach a state where like all the examples are same label, then I can stop there, make it a leaf node. Okay. Similarly, if dt is an empty set, let's say you keep splitting, at some point you reach an empty set of examples. Okay, so then you can set T to be some sort of default class. For example, like the default class in the banking application is always to be conservative, so you can just say no. Okay, then if dt contains records that belongs to both classes, right? So then we are going to find the best test to split the data recursively. Okay, now there are certain design choices that we need to make in this recursive splitting, which is what is going to differentiate different algorithms. Okay, so we're going to look at three different questions. The first question is how to specify a test. Like, so how do I come up with the test condition for each node, right? Like, so how to specify the attribute or feature test condition. That is my first question. Then once I have a bunch of tests, so how to determine which is the best split, right? Like, so how to determine the best split. Okay, then the last question is when to stop splitting. Okay, so once we have answer for all these three, then we have an algorithm which can take a data set and construct a decision tree, right? So let's start with the first question. So the first question is how to specify the attribute test condition. Okay, so I think this really depends on what kind of feature you have. Okay, you could have some sort of nominal features or categorical features, or you could have ordinal features, like which means there's an order in the feature values, or you could have simply continuous features, right? So for each of these kind of features, we need to come up with different ways to split, right? And you could also consider two-way splits versus multi-way splits. Okay, let's start with an example. For example, let's say I have a feature called car type. Okay, now this car type feature can take three values: family car, sports car, and luxury car. Okay, so now if you want to test based on this car type feature, there are a couple of possibilities here. Like, so for example, one way is multi-way split, like where you check the car type, and depending on the car type, you branch into three different directions. Like, so one for family, one for sports, and one for luxury. Okay, so this is a multi-way split, but you can also just do two-way splits. For example, like I could take car type and classify it into, like, whenever it's either sports or luxury, it goes one side, the family car goes other side. Or I could have another setup where the family and luxury cars go one side and sports car goes to other side. Okay, so when do you think this is more useful than this kind of split? Like, so when are these splits useful? So in one split, I'm grouping sports and luxury together. In the other split, I'm grouping family and luxury together, right? Any thoughts? Yeah. Yeah, well, that's when you would group, right? Like, but then, like, for what kind of problems? Sports and luxury would be similar, while what, like, other problems have family and luxury. Yeah.
Let's say if you want to calculate the insurance.
Okay. So which one is?
Luxury and sports would be more expensive.
Okay, so in insurance kind of problems, maybe it's better to split using the first way. So what about the second way? Like, so when is the second one useful? Yeah. Comfort, yeah. So then you can go for family and luxury cars, right? Like, so depending on the problem, one is better than other, right? This is why it's important that we answer the second question, which is like, what is a quantitative or objective way to decide whether this is better or this is better? Okay, so we're going to talk about that. Okay, so for now we are just deciding like what are all the different ways in which we could split. So then we will talk about how to automatically pick one out of these many splits. Yeah.
Like if you split the truth separately and you put them, it's only for like an optimization.
Yes. Yes. Okay. So now let's talk about continuous attributes, right? So if I have continuous attributes like salary, for example, the taxable income, right? So how do I split continuous attributes? Yeah. You can put them into intervals and like some sort of like discretization, right? Like, so for example, like you can take taxable income and say, oh, I want to consider less than 10K, 10K to 25K, and so on, right? Like, so discretization is one option. What are the other options? You could also come up with binary decisions. Like, so for example, I think this decision tree that we have, it has a binary decision. Like, so instead of having discrete bins, somehow the algorithm found this magical number 80K, and it says, oh, anything less than 80K is one class, anything greater than 80K is one class, right? Like, so basically we can have some sort of binary decision, okay, where you're saying anything less than V or greater than or equal to V. Then the question becomes how to find V. Is that clear? Okay, so now this is how to split, right? Like, there are, like now given a bunch of features, depending on whether it is continuous or nominal, like you're going to find different ways to come up with splitting conditions. Okay, now let's say you have all your split conditions. Now we're going to talk about the second question, which is Q2 is how to determine the best split, right? Like, so how do I, let's say there are 100 possible splits. How do I know which is the best split, where the best is defined as something that is more discriminatory, right? Like, so I want, in the end, I want good classification performance. Like, so if I out of all these 100 possible splits, which one is going to have higher accuracy or better prediction or better generalization, right? So let's take a 10-minute break, and then we'll talk about the metrics